Hi, I'm Daniel Chan from UNSW Sydney. Welcome to another adventure in pure mathematics. In this video, I want to tell you about the extension problem, which is something that homological algebra can answer very, very well. In so doing, we're going to introduce some important notions in homological algebra, that of split exactness and also of Hom-lifting. Okay, so let's start by looking at what the problem involves. So basically, we're going to fix two R modules, R's a ring here, M and N. And essentially, we want to say, well, how can we build a new module out of those modules M and N as components? So more precisely, we're going to study all possible extensions of M by N, by which we mean a short exact sequence of this from 0 to N to E to M to 0. Okay, I'll denote that short exact sequence with eta. And then the maps here will be iota and pi. Remember, this pi is surjective, this iota is injective. And one of the things about being a short exact sequence is basically it's a way of encoding the fact that essentially this module M is the quotient of E by the image of iota. And since this is injective, it's essentially saying that E modulo N, if you identify N with its image via iota, is isomorphic to M. Okay, so this E is an extension in that way. It has a submodule isomorphic to N, such that the corresponding quotient is isomorphic to M. Now, this takes a while to actually answer this question, but we're going to look at a subproblem. Okay, so the subproblem is, well, you look at this extension and there's actually lots of choices for what this E could be, but there's one that kind of stands out. It's distinguished and it's what we call trivial or split. So what's the simplest object that we can put in here? The one that perhaps first comes to mind is just to put in the direct sum. Okay, so we can put in an N here and an M here, and N direct sum M. So certainly this is a situation which has a submodule isomorphic to N, whose corresponding quotient is isomorphic to M. And to put it into a short exact sequence like this, it's quite simple. What is the map that injects N into here? You basically have the canonical injection where you just slot this into the first coordinate. So N inside here maps to N comma 0. And then the map from here to here is just projection onto the second factor, the M factor. So I'll denote that pi lower M. So NM just gets mapped to M. And of course, what is the kernel of this map? The kernel of this map is just all the tuples, pairs here, such that M equals 0. So they're all the things of this form, N comma 0, which is precisely the image of this. Okay, so here we have a short exact sequence, and that's an example of an extension of M by N. Okay, so one of the things that's a little bit funny in this case is that, of course, if you want to just say, I put together the modules N and M together, I can do this. Okay, and here in this extension, it's a little bit asymmetric. N here is the submodule and M is the quotient. Of course, when you look at this, the roles of N and M are symmetric. So of course, you could have made M the submodule and N the quotient instead. And then you also get a short exact sequence that way. So let's just put in those maps as well. Okay, so certainly you can go the other way around. So you inject M into here. So that will be iota M. And then you can just project onto the N factor here. Projection N. Okay. And this is a very, very nice property when you use all these injections and projections, okay? Basically, what you can do is you can say, well, what does it mean to express a tuple here in terms of its components, okay? So firstly, perhaps what we'll do is we're going to look at this expression here, pi m composed with iota m. So we take a pair like this, nm, we map it to m. And then if we inject that back in, you'll get 0m. So basically, what that map does here is it projects this n direct sum m onto the copy of m sitting inside n direct sum m. Okay, so send this nm to 0m. And similarly, if you do something similar, you go around this way and then back, you get this iota n pi n. So that's going to send nm to n comma 0. So it's projection onto the copy of n sitting inside the direct sum. Of course, if you add those two things together, you'll get back to the original. So that means that when you add these two functions, you just get the identity on n direct sum m. Okay, so this is some nice equation that you get, okay, when you have this trivial short exact sequence or split short exact sequence. Okay, so one thing that's very nice that you can observe is that if you're given any additive functor f, then you can just apply f, of course, to this equation. Now, in general, when you apply a functor f to a short exact sequence, it won't remain exact, okay? If f is an exact functor, then of course it will remain exact, but in general, it won't be the case. But it's rather nice that in this case, we can actually show that applying any additive functor will actually preserve split exactness, in fact, okay? So it won't preserve exactness, okay, but an additive functor will preserve split exactness. So what do I mean by that? So let's just apply f to this whole sequence here. So you get 0, since it's additive, f of 0 is 0, f of n is here, f of n direct sum m is here. The map here is just f of iota n, and then you have f of pi m here mapping to f of m, and so forth. And I claim that actually this here is essentially just the direct sum of f of n and f of m. And the way you get that is you just look at this equation and you apply f to it. So what happens here when you apply f to this? Well, the f of the identity, since it's a functor, is just the identity on f of this n direct sum m. So you've got a way of rewriting the identity functor on here. Okay, so this well, let's suppose there's a functor that goes to modules, some other module category. Okay, so this is a module, okay, f of n direct sum m, okay, and we're going to express the identity on that as a sum of two things, f of this and f of that. But since f preserves composite, this is the f of iota m composed with f of pi m plus f of iota n composed with f of pi m. So in other words, if you apply f of the composite, so you have f of this one plus f of this one, okay, you'll have a projection onto a factor that's isomorphic to this. And similarly, when you look at the other term, okay, you'll get a projection which is an isomorphism with a copy of this inside here. Okay, so that it allows you to show that this is actually a split exact sequence. Okay, so there's a little bit of thought that goes into that, but hopefully it's also a little bit clearer when I go through the next proposition. Okay, so what I want to do here is to say, well, what does it mean for a short exact sequence to be split? Basically, you want one which is either of this form or just isomorphic to this. Okay, so I want a slightly simpler criterion than just writing it out and saying it's isomorphic to this. And the answer is that there is a way to do that, and it sort of looks at just part of this picture. Okay, so if you have a part of this picture, then you can actually get this situation. Okay, so that's the content of this proposition. Let's have a look at it. Okay, so eta is split precisely if one of the following equivalent conditions holds. Okay, so what are the equivalent conditions? Well, I claim that basically all that you really need is that you need one of these two maps to exist and behave nicely. So what is, for example, this map here? So basically this is a backwards map, and what's nice about this is that, well, if you start here and you go around like this, so we went around this way before, but now suppose you start here and you go around like this, n goes to n0, and when you project back to n, you'll get back to n. So that's the identity. So here we're going to assume that if you're given this eta, this short exact sequence, suppose that there exists some map from e to n, so backwards like this, e to n, such that when you do this iota first and then go back, it's the identity on n. Okay, I claim that if this happens, okay, this will happen precisely when this is split, when this is isomorphic to something of this form. Okay, and similarly, you can also work on the other side. If you have this map and it has the property that you expect going around this way, and this is the same thing. If you do this one first and then this one, m maps to 0m there, and then when you project here, you'll get to m again. So here, if there exists a map, this time from m to e, but going back this way, m to e, such that pi composed with sigma is the identity on m, then also then it will be split. So certainly eta split implies these two because we've shown that we can take these to be what are called the splitting map sigma. Okay, and the point is that with either of these conditions here, you can prove that it will be split. So I won't give you the whole proof, I'll just sketch it so hopefully that you can see what's going on. Okay, so suppose, for example, we're given 1 and we want to show that it's split. Okay, so here's our sequence eta, our short exact sequence eta here, and we're given the splitting map sigma, which goes back from E to N. Okay, so what do we need to do? We need to find essentially an isomorphism firstly of E with N direct sum M. So essentially we need a complement to iota of N. And what's the complement of iota of N? So we've got to use a sigma somehow, and I claim the thing to use is actually just the kernel of sigma. Okay. And then if that is the correct complement so that it works like this, then when you look at that component inside here, this pi should be an isomorphism on that. So I claim the other thing is that if you restrict the pi to this kernel of sigma, that gives you an isomorphism with M. Okay, so if you have this and you have this, essentially you have to have something that's isomorphic to this sequence here. I won't go through the whole of this. I'll just say some words about roughly how it works. And it's not too difficult. There's quite a few things to prove, but let's just give some examples of what goes on here, okay? So for example, to show that this kernel sigma really is a complement, and actually not only that, but pi gives you an isomorphism of this kernel sigma to this M, okay? We can do the following, okay? So this is what we'll do. Let's suppose we want to show, for example, that this map is injective. Okay, so anything in kernel of sigma, okay, when you apply pi to it, okay, suppose it's in the kernel of this pi as well, okay, if it's in the kernel of the pi, then it has to be 0. Suppose you have something that's in the kernel of pi, then it's in the image of this iota, okay, it's in the image of the iota. So if it's also in the kernel of sigma, then when you apply the iota to that element and then sigma, you'll get 0. But iota composed with sigma, remember, is the identity. So if that composition is 0, then you must have started with 0, okay? Because you just applied an identity to it to get 0, so it must have been 0. So the kernel of this map here is just 0. And then the other thing you might want to do, and perhaps this is in many ways the key to what's going on here, is that, well, how can you know that this actually gives you a complement, okay? So also another way to think about this is, how do you know that this is surjective? Okay, so I guess the key thing here is that, well, the way you should think of this is you should think of this as part of the information here. Okay, so what happens here is you've got this piece of information. So if you go around like this, this is essentially projection onto the copy of N inside here. So what about you claim that you should get the complement, okay, and how do you get the complement? Well, you need to be able to project onto this kernel of sigma, okay, and how do you do that? Well, presumably what you do is just subtract off the component that corresponds to N, which, so in other words, you subtract off what happens when you apply the projection going around like this. And that will give you the answer and also complete the rest of that. There's a little bit to write down when you go through the proof of that, but it's not too difficult, and the main ideas are there. Okay, so that's all very well and good. Let's just sum up what we've done so far, okay? So basically, when we want to look at short exact sequences like that, and we look at some which are very special and, so to speak, trivial, okay, they're the split ones, where essentially this E is a direct sum of the submodule and quotient module, and also it works in that sort of obvious way. And we note that these are rather nice in lots of ways. Not only can you understand this module very easily, but if you apply any additive functor to it, it remains split exact, and in particular exact, because even when you apply an additive functor to an exact sequence, it might not stay exact. But in this case, it will stay exact, and in fact, it will stay split exact. Okay, so the question becomes, well, how do we actually test this? And the idea is that we have to find this, what's called a splitting function, okay? Why either we split this injection with this map here, okay? or we split this surjection with this map here. Okay, so how do we find the sigma? So let's look in the second case here. Okay, how do you find the sigma? Okay, so how can you find sigma as in proposition 2? So I'm going to rephrase this in terms of what's called Hom-lifting, which is a very important concept in algebra and mathematics more generally. Okay, so here's our short exact sequence here. And then what we're going to do is we're going to look at the identity map from M to M. Okay, so that's what we have on this side, on the right-hand side, identity from M to M. So we've got the pi here, there's the pi, and basically what we want to do, we want to find the sigma. So the question that we're asking really is, can you find a sigma which goes from M to E? A sigma, question is, does there exist a sigma going from there to there, such the composite like this is this one there? So this is what's called Hom-lifting. Hom-lifting, you map from here to here, you have a homomorphism like this, but can you lift it to a homomorphism like this? And lift this means that not just any map from here to here, but a map from here to here such that when you compose it with this one, okay, you get this one here. So this one lifts to here like that. Okay, so that's all very well and good in terms of what we have here, but now I want to relate it also to the Hom functor, okay, because we're looking at homomorphisms, so you should use the Hom functor. So what we're going to do is we're going to take this short exact sequence and we're going to apply the Hom functor to it. Let's apply that Hom functor. So you get Hom of M into this sequence here. So you get 0 here, Hom R of M into N, then Hom R of M into E, then Hom R of M into M. This will also go to, if you add this one here, to 0. But remember, Hom is only left exact. So at least this bit here is going to be exact. Okay, so the last map here, that's the one that we're going to concentrate on. I'm going to denote, it comes from pi, so it comes from letting this Hom functor act on pi, so it's going to be denoted pi lower star. Okay, so what's going on here? Okay, so the key point is that we can reinterpret this diagram and the problem that we're asking here in terms of elements of this exact sequence here. Okay, so firstly, here we have the identity map, identity on M inside here. Okay, and what's this map here, pi lower star? Well, what this does is it takes a homomorphism M to E, okay, and then to get a homomorphism M to M, it composes it with this. So basically, you want to say, does there exist, so this is question mark, sigma in here, such that this maps to the identity on M. That's what you want to ask. Okay? So remember, if you had a 0 here, you know that this would be surjective. But in general, this is only left exact. So this is not necessarily in a surjective map. Right? You have an element inside here. And if you can actually hit this element with some sigma, okay, then you know that this sequence eta will split. Okay, so that's rather nice. So the useful observation here is, well, the easiest way to know that you can find such a sigma is if pi lower star is actually surjective. Okay, and what's one such instance where it's surjective? Well, if the Hom M blank functor is exact, then that's true, and that's equivalent to the fact that M is projective. So in other words, if M happens to be a projective module, so if you have a projective module here, so in particular if it's a free module, okay, then we'll know that this pi lower star is always exact, surjective rather, and since it's surjective, you can find something, a sigma inside here, okay, which hits this identity of M. In other words, you can lift the identity of M to a homomorphism from M to E, and hence split this short exact sequence. Okay, so this is a very, very nice result, is that if you have any short exact sequence like this, and the last term here just happens to be projective, then it will split. And if it splits, that means that this will be a direct sum of this module and this module. And also, if you apply any additive functor with it, it will stay split exact. I hope you enjoyed this adventure in pure mathematics.